Across the globe, bridges stand as marvels of human ingenuity, defying gravity and nature to forge connections between distant shores and rugged landscapes. From the rustling cables of the world's longest suspension spans to the sleek silhouettes of cable-stayed icons, these structures are more than mere thoroughfares. They are expressions of art, science, and ambition. Behind their elegant profiles lies a tapestry of cutting-edge materials, precision engineering, and logistical orchestration so intricate that even the smallest miscalculation can ripple into costly delays or safety hazards. In this video, we peel back the curtain on the secrets that enable engineers to stitch continents together, spanning rivers, valleys, and seas with frameworks that endure wind, waves, and the relentless march of time. Defining largest. When discussing the world's largest bridges, it's crucial to clarify which measure reigns supreme: total length, main span, height, or deck area. The Danyang-Kunshan Grand Bridge in China claims the title for sheer length at nearly 165 kilometers, traversing rice paddies, waterways, and viaducts in its colossal stretch. Japan's Akashi Kaikyō Bridge holds the record for the longest uninterrupted span, almost 2 kilometers of deck suspended between its towers. France's Viaduct, soaring more than 340 meters above the Tarn Valley, stakes its claim as the tallest vehicular bridge. Meanwhile, the Hong Kong-Zhuhai-Macau link, with over 55 kilometers of combined bridges, tunnels, and artificial islands, boasts the greatest deck footprint. Each category presents unique engineering puzzles demanding bespoke solutions. Secrets of suspension giants. Suspension bridges achieve their graceful, swooping forms through a delicate balance of forces. Massive main cables, each composed of thousands of galvanized steel strands, are spun on site in loops or assembled from pre-waxed bundles, then draped between towering pylons before anchoring deep in bedrock. These cables are often housed in sealed, dehumidified casings that purge moisture and inhibit corrosion, securing service lives beyond a century. The deck itself employs H-section stiffening girders, a cross-section optimized to resist bending while minimizing weight. Segments are fabricated off-site, floated into position on barges, then welded continuously to form mile-long spans. After Tacoma Narrow's collapse in 1940, modern designs undergo iterative wind tunnel and computational fluid dynamics (CFD) testing. Deck fairings are sculpted to reduce vortex shedding, and tuned mass dampers nestled in towers siphon oscillatory energy into hydraulic fluids, ensuring even typhoon-force winds leave the bridge steady. Cable-stayed colossi. For spans in the mid-range, roughly 300 meters to 1,100 meters, cable-stayed designs have surged in popularity. Instead of draping cables, these bridges fan straight, parallel strand stays from pylons directly to the deck, resembling immense steel harps. Each stay is tensioned and monitored individually, allowing engineers to fine-tune load distribution and isolate maintenance to single tendons. Construction often leverages spider-like climbing cranes and robotic stay installation units that ascend the towers, feeding and stressing each strand with millimeter precision. Hybrid composite decks, melding steel girders with high-strength concrete slabs, deliver unmatched rigidity at reduced weight. On Russia's Russky Bridge, the world's longest cable-stayed span at 1,104 meters, engineers used automated tensioning and real-time alignment sensors to achieve record tolerances, proving that with orchestration worthy of a symphony, cable-stayed elegance can rival suspension might. Viaduct and causeway marvels. When nature demands distance over flat water or swampy marshes, viaducts and causeways emerge as the pragmatic heroes. The balanced cantilever method extends box girder segments outward from each pier in equilibrium, stitching the deck together mid-span without extensive falsework. France's Millau Viaduct used this technique to leap 50 meters per lift, spawning a continuous ribbon of concrete high above the valley floor. Meanwhile, China's Danyang-Kunshan Grand Bridge marshaled the incremental launching method, ILM. Entire deck sections cast at one end of the span were slowly pushed forward over temporary rollers, covering dozens of kilometers with accuracy measured in millimeters. In the Hong Kong-Zhuhai-Macau corridor, artificial islands anchor a 6.7-kilometer subsea tunnel. Geotechnical models accounted for buoyant soils and marine currents to prevent uplift, while GPS-guided gantries coordinated hundreds of deck placements daily. Mastering foundations and geotechnical challenges. Beneath every colossal span lies the silent heroism of its foundations. Deep caissons, sometimes exceeding 60 meters in diameter, are sunk through soft sediments until they bite into bedrock, safeguarding piers against scour and settlement. In unstable river deltas or clay-rich seabeds, engineers deploy diaphragm walls, reinforced concrete barriers installed before excavation, and employ jet grouting or ground freezing to stiffen the soil around shafts. Suspension bridge anchorages harness rock-anchored tendons, drilled dozens of meters into solid bedrock, and tensioned against massive concrete blocks. Embedded load cells continuously monitor elongation and corrosion rates. In seismic zones, base isolators, rubber bearings with internal lead cores, allow piers to shift laterally during an earthquake, absorbing tremor energy while preserving the superstructure above. This hidden realm of geotechnics ensures that, from the seabed to the sky, each bridge stands on a foundation as steadfast as human ambition itself. Aerodynamics and wind, taming invisible forces. No discussion of mega-bridges overlooks the invisible power of wind. Physical scale models, often at 1 to 200 or 1 to 100 scales, are tested in wind tunnels fitted with gust generators and tuft flow visualization, capturing the nuances of vortex shedding and buffeting. CFD simulations complement these tests, refining deck fairings and perforated barriers that break coherent airflow and disrupt harmful vortices. Vortex-suppressing strakes, small, fin-like protrusions, are tuned to the bridge's natural frequencies, quelling oscillations before they amplify. Hydraulic shock transmission units, akin to automotive dampers, are installed at expansion joints, resisting sudden displacements caused by gusts. Meanwhile, tuned mass pendulums hidden inside pylons resonate out of phase with deck movements, converting kinetic energy into heat and ensuring that today's spans stand firm even in hurricane-force gales. Material innovations, from steel to smart composites. The materials powering these spans have evolved dramatically. High-performance steels, microalloyed with vanadium, niobium, and titanium, achieve yield strengths exceeding 800 megapascals, slashing girder weight without sacrificing ductility. Ultra-high-performance concrete, UHPC, reinforced with steel or synthetic fibers, delivers compressive strengths north of 150 megapascals and resists abrasion, freeze-thaw cycles, and chemical attack. Experimental fiber-reinforced polymer, FRP stays, composed of carbon or glass fibers, promise corrosion immunity and ultra-low weight. Ongoing trials assess long-term creep under sustained loads. Below the waterline, sacrificial anode cathodic protection systems and impressed current networks shield steel components from electrolytic corrosion. Meanwhile, self-healing concretes, imbued with microcapsules of epoxy or calcite precipitating bacteria, stand ready to seal hairline cracks autonomously, extending service lives into centuries. Construction recreation, how they build the impossible. Erecting structures that tower hundreds of meters or extend across oceans demands logistical ballet on a monumental scale. Heavy-lift barges and cranes with capacities exceeding 1,000 tons hoist prefabricated deck segments into position, guided by real-time kinematic GPS and active motion compensation systems that neutralize wave and sway. Climbing formwork jacks ascend piers ring by ring, pouring concrete into molds that rise day by day without external scaffolding. Self-launching gantries, spanning multiple piers, operate on rails or cable systems to place beams and deck units autonomously, knitting the superstructure together in a dance of steel and concrete. Laser-guided total stations lock each module into place with millimeter precision. In busy waterways or highways, entire deck sections are slid into position during brief nighttime closures, reopening for traffic by dawn to minimize disruption and maintain project momentum. Smart monitoring and lifelong maintenance. The story doesn't end once the ribbon is cut. Embedded structural health monitoring (SHM) networks relay strains, accelerations, temperatures, and displacements in real time to centralized control centers. Machine learning algorithms sift through terabytes of sensor data to detect anomalies, a slackening cable stay, an unusual vibration mode, or unexpected pier settlement, well before they pose risks. Unmanned drones equipped with LiDAR and high-resolution cameras scan deck undersides and pylons, generating detailed 3D point clouds that reveal corrosion, fatigue cracks, or material degradation at millimeter scales. Digital twins, virtual replicas mirroring every rivet, tendon, and joint, simulate long-term aging and forecast maintenance needs, shifting bridge agencies from reactive repairs to proactive interventions. This fusion of sensors, robotics, and predictive analytics ensures that megabridges remain safe and serviceable for generations. Environmental and social considerations. These megaprojects often traverse ecologically sensitive zones and densely populated areas, demanding careful stewardship. Comprehensive environmental impact assessments, EIAs, model hydrodynamics to position piers away from critical fish, spawning grounds, and coral reefs, while construction windows are timed to avoid migratory bird seasons or marine mammal breeding. Causeway embankments incorporate fish passages and mangrove restoration areas to maintain ecosystem connectivity. Socially, bridges can transform local economies but also generate noise, visual intrusion, or displacement. Engineers and planners engage stakeholders through town halls, participatory design workshops, and transparent grievance mechanisms, ensuring that community voices shape mitigation measures. Some bridges feature public promenades, observation decks, and cultural pavilions, turning infrastructure into civic space. Carbon offsets, renewable energy credits, and on-site solar installations aim to drive the net zero ambitions of 21st century bridge building. The future of mega bridges. What comes after kilometer-long spans and sky-piercing viaducts? Engineers are exploring floating cable-stayed decks that dynamically adjust tension via shape memory alloy actuators and retractable segments that slide aside to admit supertankers guided by autonomous control systems. On-site 3D printing robots may soon fabricate piers and girders layer by layer from UHPC mixes, slashing formwork waste and labor costs. Smart materials. Self-healing concretes and fiber-optic embedded composites could enable bridges to autonomously seal microcracks and relay detailed health data. Climate-adaptive designs envision spans that rise with sea level changes or shift laterally during storms, preserving both structure and habitat. Integrated renewable energy harvesting, from solar canopies on deck to micro-wind turbines in pylons, aims to make future bridges net zero power producers. If you found this bridge building secrets as fascinating as we do, don't forget to hit the like button and be sure to subscribe so you never miss an update on the latest feats of engineering, design, and innovation. Thank you for watching and see you next time.